Hi students, in the previous video I have given you the same question, same type of question. Okay, but it was the question was different. Here, if we apply a force here in the downward direction, the displacement was y, and he is asking to find out the force in terms of the spring constant. Here the spring constant is k, here also k. Okay, now the spring constant k, and in terms of y. Okay, now he, in that question we found that f value in terms of k and y. Okay, force. But now here in this situation, in this question, we are going to find the time period of the blocks in both the cases. We need to find out the time period of the blocks. Here in this situation, both the blocks are connected here. Now we need to find out the time period of it. So as soon as you hang it, what happens? Due to its weight, it comes to downwards to a distance of y naught. Am I right or not? Even here also it comes to a distance of y naught. It comes to a distance of y naught in the downward direction. Yes, so it comes to a distance of y naught in the downward direction. Then after that it comes to equilibrium position. See, because of its weight, it comes downwards, and there it comes to equilibrium. Even here also, because of its weight, it comes downwards and there it comes to equilibrium. Then after that, still if we just pull it to a distance of y and release, then what happens? It sets into oscillations, like it does simple harmonic motions. Am I right or not? Even here also, it when we just pull it to a certain distance y, further distance y, and release, then what happens? It will be in simple harmonic motion. Am I right or not? Then it will have a certain time period for that simple harmonic motion, right? Then if you want to find the time period, then we have to follow certain steps to find out. First one, apply equilibrium condition. Equilibrium condition means what? Suppose if here itself, if we hang, as soon as we hang the mass to it, then automatically due to its weight it comes downwards to a displacement y naught and it comes to equilibrium. So now let us find out the equilibrium condition first, and we have to write the equilibrium condition. Should write the forces. Okay, now, and the next one, what we have to do, after coming to equilibrium position, we need to displace it to a certain distance y. It's not y naught, it is y. Okay, it has to be displaced to a further distance y. Then again what happens later? If we just pull it to a distance y and release it, then it comes into simple harmonic motion, and there we need to find out the net force. When we just pull it to a distance y, we need to find out the net force. This is the process. Okay, now, so first let us calculate in the first case. Let us calculate here, applying the equilibrium condition in the first case. Then we can write it as, suppose if it comes to downwards, then you will write it as downward force is equal to mg and upward force is equal to tensional force. Here t, here t, therefore t, mg is equal to t. This is the equilibrium condition when it comes down. Am I right or not? Mg is equal to t, upward force equal to downward force. In such case, then what will be the elongation in the spring? Suppose if it comes to a distance of y naught, then the spring will be elongated to a distance of y naught by 2, as we have discussed in the previous video. You can see my previous video so that you will have an idea. Okay, so mg is equal to t we have applied, and can you tell me what is the tensional force at this point? The tensional force at this point is, see here it is 2t. Am I right or not? It is 2t. Okay, so because of that 2t tension, okay, because of the 2t tension, in that restoring force is being developed and its value is k into y naught by 2. Am I right? So from this, how do we write the tensional force? T is equal to k y naught by 4. This is a tensional force. Do you understand? And now if this is a tensional force, now what happens? We have written all the equilibrium conditions. Now what we are going to do? Okay, now we should displace it. Second step, we should displace it to a further distance y. So we should displace it to a further distance y. And when we displace it to a further distance y, then automatically the tensional force changes, no? So when we displace it to a distance y, okay na, then what happens here? You can write it as here T dash will be developed here. Assume that the tensional force is T dash. Therefore, here 2T dash. And now I am going to write the 2T dash. 2T dash is equal to, now what will be the extension here? Actually, here extension is y naught plus y. Therefore, here extension will be y naught plus y by 2. The total extension in the spring is y naught plus y by 2. So from this, we can write the tensional force as T dash as y naught plus y by 4. Y naught plus y by 4. This is about T dash value. Okay, now when we still pull it to a distance of y, then tensional force changes, no? That is T dash we are assuming. Now again, suppose if this m is there, no? Because of net force, okay, now it is gaining certain acceleration initially, right? So if we calculate the net force, the third step is that only find the net force and then write the time period, right? So I'm going to find the net force here. How to find the net force? That is mg minus, mg is the downward direction, is in the downward direction, and in the upward direction the tensional force is T dash. Yes or no? Right. Therefore, mg minus T dash means what? Y naught plus y by 4. I'm sorry, it is here it is k into y naught plus y by 2, no? Yes or no? 2T dash is equal to k into y naught plus y by 2, and that's why it is k. Here also it is y naught plus y by 4 into k. Yes or no? This is a restoring force. Restoring force F is equal to kx, no? That is what we have written here. So mg minus y plus y naught by 4 into k. Now what is mg here? mg can be written as t here. So t can be written as k into y naught by 4, no? So k into y naught by 4, instead of mg I am writing is equal minus okay, k into y naught plus y by 4, that is equal to k into y naught by 4 minus k into y naught by 4 minus k into y by 4. Therefore, ky naught by 4 gets cancelled. What is f net here? F net is equal to minus ky by 4. See here we have written f net. Then what is the time period formula? T is equal to 2.2 square root of m by k. K is what here? K by 4. K is what? K by 4. Therefore here the time period. Here it's not tension, it is time period. Time period T is equal to 2.2 square root of 4m by k. This is in the first case. Okay. Right. Now let us see the second case. In this second case, okay, first what we have to do, immediately as soon as we keep the block to this, then immediately due to its weight it comes to y naught distance and it comes to equilibrium position, right? So when it comes to equilibrium position, then we can write it as mg is equal to k into mg is equal to upward force is nothing but 2t here. Yes or no? Why? Because here tensional force, therefore here the tensional force is 2t. So mg is equal to 2t. And now let us take the spring here, and the restoring force in the spring can be written as, restoring force is nothing but the tensional force here. T can be written as k into, suppose if it is displaced to y naught distance, then what is the displacement of this spring here? We can write it as it is 2 into y naught. 2 into y naught. Therefore, t can be written as 2k into y naught. Okay, now this is t. Now substitute the t in this equation so that you will get mg is equal to 2 into t. 2 into 2k y naught, which is equal to 4k into y naught. This is the equilibrium condition that we have applied. Now next what we have to do, if we just apply a small amount of force, if we apply a small amount of force and displace it to a distance y, a small distance y further. Okay, now initially it was y naught, still if we are increasing it to a distance y and releasing. So when we just pull it to y distance, then automatically tensional force changes, no? Therefore, we can write it as here, when the tensional force changes, then here 2t dash will be there and here t dash will be here. Yes or no? T dash will be here, no? Then what is a restoring force developed in the tension, developed in the spring here? That is when we pull it to a further distance, y downwards, still if we pull it to a distance y, then here what will be the elongation in this spring? Suppose if it is y naught, then it is 2y naught. If it is y naught plus y, then it is 2 into y naught plus y. Am I right or not? Then the elongation in the spring is 2 into y naught plus y. Therefore, tensional force T dash is equal to, it can be written as k into okay, k into 2 into y naught plus y. This is the elongation in the spring. Am I right or not? Here the displacement of this block is y naught plus y. So that the elongation in the spring will be 2 into y naught plus y. Yes. So it is T dash. Now let us apply the net force. Let us find out the net force here. Net force F net is equal to mg minus mg downwards, and the upward force will be 2t dash, so that you will get it as mg minus 2 into 2k into y naught plus y. What is mg here? Mg is equal to 4k y naught, no? So 4k y naught minus 4k into y naught plus y, which can be written as 4k y naught minus 4k y naught minus 4k y. Therefore, 4k y naught minus 4k y naught gets cancelled. Therefore, F net we have calculated. With that F net, it accelerates first. Am I right or not? Minus 4k y. So we have got the relation. This is nothing but simple harmonic motion. Why? Because F is equal to minus kx. Okay, now if it is like that, then time period of this will be t is equal to 2 pi into, it is time period, it's not tension now. Time period is equal to 2 pi into square root of m by, what is the k here? K value, effective spring constant, now we have got 4k. Therefore, t is equal to 2 pi into square root of m by 4k. This is in the second case. Okay, thank you.